In the first part of this chapter on roller coasters, we're going to look at circular motion. Now, to understand circular motion, we want to use a lot of concepts that you've learned in other courses or earlier in this course. Velocity is displacement over time, so anytime we're looking at the velocity of an object, remember the equation. Velocity equals displacement over time. So we'll be using that equation frequently. Acceleration is any change in velocity. Remember acceleration, change in velocity over time. We'll be looking at forces, Newton's second law, F net equals ma. We'll dealing a lot with circular geometry. Whenever we have a circle, we have the radius of the circle, the distance from the center to any point on the circle, the diameter of the circle, which is twice the radius, from one point of the circle to another point of the circle through the middle, and the circumference, the distance around a circle. The circumference is 2 pi r, or pi d. Now, when talking about circular motion, we're going to be looking at the difference between rotations and revolutions. When we think about a rotation versus revolution, we need to think about the axis, the straight line around which a rotation is taking place. Rotations are any time you turn around an internal axis. So if you spin around in place like a figure skater doing a spin or a diver doing a spin, they are rotating. If you're doing a flip, you're rotating around an internal axis. The Earth rotates. It rotates around an axis that goes through the North and South Pole. It rotates once every 24 hours. A revolution is when you go around an external axis. So you're going around an external point, like the Earth going around the Sun. The Earth revolves around the Sun once every 365.24 days. Now, one of the key things we're going to talk about is speed when it comes to circular motion. We're used to dealing with linear speed, displacement divided by time, or distance divided by time in terms of speed. For circles, there's two types of speed. There's tangential speed. So if you're going around a circle, at any point, you are moving tangent to the circle, tangent being a line that touches the circle at one point. If you move to a different point in the circle, that tangent goes in a different direction. And this is how we remember that going around a circle, we're constantly changing direction. The tangential speed is how fast you'd be going in a straight line at that point. The rotational speed is how many rotations there are per second. That's known as a frequency, and usually done in rotations per minute, RPM, or hertz. A key new variable we're going to look at is period. Period is the time it takes to complete one revolution or rotation. This is the opposite of frequency. So you can relate period and frequency. Frequency is 1 over period, or period is 1 over frequency. So the number of times revolutions per unit time is frequency, or rotational speed. Period is the time it takes to complete one revolution. They're the opposite of each other. Period is capital T versus little t, which was time. So period, the time it takes to complete one circle. Now, when we're describing circular motion, the key to circular motion is that you are always accelerating. Remember, acceleration can be any change in velocity or change in direction. Change in velocity is a change in direction. Velocity being both speed and direction. So if you're speeding up or slowing down, that's a change in velocity. If you are changing direction, that is a change in velocity. So in circular motion, you are always accelerating. That acceleration is always pointed towards the center of the circle. So when you're going here, your acceleration is always pointed in towards the center. Even assuming you're moving at constant speed around the outside of the circle. That means the force must also be pointed towards the center, and this is known as centripetal force. Many people also use the term centrifugal force. This force does not really exist. This is the force that people talk about pulling to the outside of a circle. The reason when you're going around a circle you feel like you're being pulled to the outside is due to inertia. You want to keep going in a straight line. That straight line path takes you to the outside of the circle until something applies a force towards the center of a circle. We think of a washing machine. In your washing machine, it spins to get the water out of the clothes. There are small holes in the drum of the washing machine. As it spins, the water gets the outside of the drum because there's no force on the inside to keep it from, to cause it to go towards the center. So the drum pushes it to the center, but there's small holes in the drum. So every time it hits a hole, there's no force to push it to the center, and it flies in a straight line out of the circle. So it would go out of the drum. The clothes are big enough they don't go through the holes, and the clothes stay in, have a force towards the center, the centripetal force, causing them to go around in a circle. Think about a rope on or a ball on a string. If you were going to spin it in a circle, you would use your hand as the center point. You'd be applying a force towards the center of the circle. Now the equations for circular motion. The first equation, centripetal acceleration equals v squared over r. This is a little hard to see here, sorry. We commonly refer to something as g's. G's are the number of times greater than the acceleration of gravity. So if you take the acceleration, divide by 9.81, that would be the number of g's. If you hear someone saying they're 4 g's, they're 4 times larger than the acceleration due to gravity. Centripetal acceleration will be found by doing the velocity of the object squared divided by the radius. The speed of something around the circle, remember our equation v equals delta x over t. Well, delta x here is the circumference of the circle, 2 pi r, and t is the period of the circle. So it's 2 pi r over capital T. And remember force, F net equals ma. So Fc, centripetal force, is the mass times the centripetal acceleration, or the mass times v squared over r. And you can put 2 pi r over t in for v squared and get another version for pi squared r over t squared. So these are all 3 versions, the same thing with 3 different versions of the centripetal acceleration. Now let's look at some example problems with circular motion. 13-gram rubber stopper is attached to a 0.93 meter string. The stopper is swung in a horizontal circle, making 1 revolution in 1.18 seconds. Find the tension force of the string. So we know a couple of things. We know the mass is 13 grams, which is 0.013 kilograms. We know the radius is going to be 0.93 meters because you're holding one end of the string, the stopper's on the other, so that's making up your radius. And your period is 1.18 seconds. So we need Fc equals mass times centripetal acceleration. To find the centripetal acceleration, we need the velocity. Velocity is 2 pi r over t, so 2 times pi times 0.93 divided by 1.18. So we get 4.95 meters per second. Now for a circle, AC is going to be v squared over r. So 4.95 squared divided by 0.93. Which is 26.3 meters per second squared. So Fc will be 0.013 times 26.3, which means we have a tension force, a centripetal force, which is our tension force because it's a string, 0.34 newtons. You could have also used the Fc equals 4 pi squared r over t squared times mass to solve this with one equation. Runner is moving a speed of 8.8 meters per second, rounds a bend with a radius of 25 meters. What is the acceleration of the runner? And what agent causes this acceleration? So part A here, we're looking for acceleration. We know acceleration is v squared over r. So 8.8 squared divided by 25. This person has an acceleration of 3.097 meters per second squared. What's causing the acceleration? Now, if the person's running, they're pushing off the ground. They may be there may be some normal force pointing towards the center. There's also the friction of their shoes. Think about trying to run on a surface with no friction, like ice, and you would slide. In this case, where there isn't ice, that you would have that frictional force to provide the centripetal force. Racing a flat racetrack, a car going 32 meters per second rounds a 56 meter curve. What is its acceleration? So A equals V squared over R. So 32 meters per second squared divided by 56. And we get 18.3 meters per second squared. Now, we want to know the minimum coefficient of static friction. We know friction is going to provide the force into the center of the circle. We're going to have a normal force. We're going to have a gravitational force. We know the gravitational force will be 9.81 times the mass. We don't know the mass here. We know the normal force will therefore be 9.81 times the mass. We know the frictional force will therefore be the coefficient times the normal force. So the frictional force will be the coefficient times 9.81 m. Frictional force is the one pointing towards the center of the circle, so it will be our frictional force is the one pointed towards the center of the circle, so it will be our centripetal force. So mass times centripetal acceleration, 18.3, equals mu times 9.81 m. Divide both sides by 9.81 m. The m's cancel, which will give us our mu, which is 1.86. So this would be a very large coefficient of friction. Seeing as most tires have a coefficient of friction around 0.9, this car would not be able to make this turn at that speed and that radius with normal tires. Okay, there's some examples of centripetal force and circular motion. We will do a number of example problems in class, and then we will move on to apparent weight.